Hey there, folks. Let's go over the problems on test 1. That's what I thought. Let's see. I don't know. Okay, let's go over these things. We went over this in class, but I want to go over it here too, so you have a record of it. Problem 1 says particular brand of shirt comes in 8 colors. That's 8 options there. Has a male and female version. That's 2 options there. And comes in 5 sizes for each gender, which is basically saying there's a number of compatible ways you can get this shirt. How many different types of this shirt are made? And this is a straightforward fundamental counting principle problem. You've got 8 different colors. You've got 2 different styles for different genders, and 5 sizes. It's a task that involves a series of selections, so it's 8 times 2 times 5, 80. That's very straightforward. I think people made that actually a lot harder than it needed to be. Problem 2, how many words with 5 lowercase letters do not contain any repeated letters? Well, again, we've got things that occur in order, 5 slots. We can use fundamental counting principle and say 26 for this one, 25 for that one, 24, and so on. It's a straightforward permutations problem, though. It's 26 pick 5, which is, and I need to just use my pen here, 26 factorial over 26 minus 5 factorial, and you do the work on that, and it comes out to be 7,893,600 different words. Okay. Problem 3, how many words with 5 lowercase letters that have exactly 3 letters that are K. So the first thing we have to do there is pick the positions, and it's not actually a pick, it's a choose. Choose the positions that have a K in them, because it doesn't matter what order they're chosen, right? They're all going to be Ks. And then we'll pick non-K letters for the other 2 positions. So there's 5 choose 3 ways of choosing where the K's go. And then for the other 2 letters, which do occur in order, 25 options and 25 options. Okay? So you do all that out, it works out to be 6,250 different words. And then problem 4, how many words with 5 lowercase letters have K appear at least 3 times? Now, this is 3 times or 4 times or 5 times, right? So what you can do is just do those 3 calculations, and actually we've done the first one for exactly 3 times. That came from the previous problem. With K appearing exactly 4 times, you have to pick choose the 4 positions that the K is in, and then pick the other letter. And there's only one way to get exactly 5 Ks, and that's just have all Ks. So adding those 3 numbers together, 6,376 words. An alternate way of working that problem would be to say, well, let's take all the words we have, which is 26 to the 5th power, 26 times 26 times 26 times 26 times 26, and subtract the ones that are not at least 3. So 0 words with K, that's 25 to the 5th. And exactly 1 time and exactly 2 times. Okay, and subtracting those away from the total will also get you this answer. Okay. Problem 5 was one that perhaps was a little challenging, but you need a few of these that make you think a little bit. Palindrome is a string of letters that is the same when the order of the letters is reversed. So how many palindrome strings of length n can be constructed using lowercase letters? And I didn't give you the number n. I'm letting n be a variable. So think about it. If n is 1, you've got 26 options of 1-letter words that when you put them in reverse order, it's the same word. When n is 2, you still have 26 because you get to pick a letter on one side, but then that fixes the letter on the other side. So it's still 26. When n is 3, you get to choose maybe the first one and the middle one, but then this one is chosen by that one. So it's 26 squared. And also when n is 4, you got 26 times 26, but then this one has to be the same as that one. This one has to be the same as that one. So what you see happening here is you kind of have a thing happening when they're odd and a thing happening when they're even. you can write it out like that. You can say when n is even, there are, and you just take the number and divide by 2, right? 2 divided by 2 is 1, 4 divided by 2 is 2. And if it's odd, you're going to have to, like 1 over 2 is a half, but you got to get up to 1. So add a 1, then divide by the 2. So 1 plus 1, and then divide by 2, and 3 plus 1, then divide by 2. There's a couple other ways you can say that together if you want to. If you want to use floor like we've used in previous problems, go ahead and bump it up 1, and then divide by 2, and then take the floor. So like 1 plus 1 is 2, 2 divided by 2 is 1, the floor of 1 is 1, 26 to the 1. And then 2, this is 2 plus 1, 3 over 2, take the floor of that, that's 1, 26 to the 1. Or if you want to use ceiling, which is something we talked about after the test when we started doing pigeonhole principle, but if you were aware of it previously, I'll let you use it, then it's just n over 2, take the ceiling of that. Right, 1/2, take the ceiling of that, you get 1. Right, and 2 over 2, 1, so on. Okay. Problem 6 says, okay, suppose that the faculty of a mathematics department is made up of 30 men and 15 women. How many ways can they form a committee of 6 people? Well, there's 45 of them. A committee that has no order in which people sit on, it's just a group of people. So it's a combination of length 6. So just do the arithmetic on that. You end up with 8,145,060 ways. Problem 7, I'll alter the question slightly to say, well, okay, suppose that the committee has to have more women on it than men. So again, you have to go back and look at each of these cases separately and add them up. It can't have 3 and 3 because you got to have more women than men. So it could have exactly 4 women. That is, we choose the four women out of the 15, and then we have to choose the 2 men out of the 30. And this is fundamental counting principle. That's the reason we multiply this. We're doing a task that involves a series of selections. We have to choose the women and then choose the men. And that's 593,775. Exactly 5 women. We choose 5 women out of the 15, and then there's 30 guys to choose from. Pick one. And so we get 90,090. And exactly 6 women, well, just choose 6 women out of the 15. So adding all these cases up, you get 688,870. Problem 8, we have the question, how many different words can be made using all the letters in abracadabra? We have now things in order. We have fixed repetition of certain things. So this is going to be a multinomial coefficient where we've got 5 A's, 2 B's, 2 R's, 1 C, and 1 D present in this word. So that's 11, multi-choose 5, 2, 2, 1, and 1. And so do the arithmetic there, 53,160 words. 9 is probably the other problem where I had you thinking just a little bit. We worked on 1 or 2 like this, but I threw you a little curve on it. How many positive integer solutions, A, B, C, and D, are there to this equation, where the sum of them is 12? And now the curve that I threw you is the positive, right? If I would just say, you know, how many whole number solutions are there? I've got 12 singles here. I've got 4 bins I can put them in, 4 types that we're going to assign to each of those. So that would be a straightforward multi-set, 4 bins, multi-choose 12. But because I'm saying positive, you need to go ahead and place 1 in each of the bins, right? So instead of 12 things left to reassemble here, you're only going to have 8. So this is 4 multi-choose 8. That's 8 stars and 4 minus 1 bars. Choose the location of the stars. That's 11 choose 8. So there's 165 solutions. And then 10 is a straightforward multi-set problem. It says, how many ways can we form a bouquet of 16 flowers using red roses, yellow roses, chrysanthemums, and hydrangeas? So 4 types. We want our bouquet to have 16 flowers in it. There's no order to the flowers whatsoever, but there is repetition unlimited repetition up to 16 of each of these different types. So that's 4 multi-choose 16. So 16 stars, 4 minus 1 bars. We have to choose the location of the 16 stars. So this is 19 choose 16, which according to my calculation is 969 different bouquets. Okay. 11 and 12 are variations on this theme, except we put some restrictions, right? With 11, we say, okay, same situation, but how many ways can we form the bouquet if we must include at least 4 red roses and at least 2 hydrangeas? Well, it's like the previous problem we did, problem 9. Go ahead and put those in there. So we put the 4 red roses in, the 2 hydrangeas, and then we worry about the other 10 flowers in the bouquet. So that is 4 multi-choose 10. That's 10 stars with 4 minus 1 bars, or 13 choose 10. Choosing where the 10 stars go is 13 choose 10, and that works out to be 286 different bouquets. And then the last problem is what we call what I call an at most multi-set problem, because we limit the number of things we could put in instead of saying you have to have at least this many. At least this many is easy. Just go ahead and put them in there, right? But when we say at most, we have to involve the principle of inclusion-exclusion. So we'll let our universal set here be the set of all the bouquets with 16 flowers of these types. R will be a subset of that with at least 9 red roses. Now this is because this is the complement of at most 8 red roses. And so the complement of at most 6 would be at least 7 yellow roses. And the complement of at most 10 chrysanthemums is at least 11 chrysanthemums. And I didn't do anything with hydrangeas because there are no limits on those. We ignore that as a limitation. So we've already calculated the number of things in our universal set. That was the 969 from problem 10. To calculate the things in set R, where you've got at least 9 red roses, go ahead and put those 9 in there. So that's 4 multi-choose 7, which comes out to 120. For the cardinality of things in Y, we go ahead and put the 7 red roses in there. So that's 4 multi-choose 9, which turns out to be 220. And then the set with at least 11 chrysanthemums, go ahead and put those in. So that's 4 multi-choose 5, which works out to be 56. Now we have to count intersections of 2 sets. If we say I want at least 9 red roses and at least 7 yellow roses, well, that actually takes up all the roses. So there's only one way to do that. Just put them in there, right? And actually, if you do the arithmetic, that's the answer you get. For red roses and chrysanthemums, because you got to have at least 11 chrysanthemums, both of these intersections are going to be too many flowers. You end up with something of length negative, and those are always 0. So 0 here, 0 there, and if we try to do the intersection with all 3, 0 there. So the cardinality of the intersection of the complements is actually the cardinality of the union complement, which is cardinality of the universal set minus the singles plus the doubles minus the triples. So you do this little arithmetic problem here, 574 bouquets. Okay, that is a review of our test. Hopefully that helps you study for our final, which is Monday morning. And I will see you in the morning. We'll continue going over the remaining pigeonhole principle problems and then talk a little bit about our final. See you then.